not try to use too much the microphone. The room is small, but I may have the bad habit of not taking enough enough loudly. Sorry. So just let me know if this happens, especially for people in the back. So today I will not talk of finite rate of innovation. I will talk about something that has obsessed me for some time now, which is what I call linear exponential threshold. So for a mathematical audience as here, so then you will think that everything is trivial for this, because you will see that it boils down to solving linear system of equations. So what's the point? Okay, that's, you see actually what is interesting in this, this approach is precisely that it's a kind of way to do nonlinear processing by solving only linear system of equations. So in the end, it looks like that. So I will not make a joke about the title itself, linear expansion of thresholds, because it's a linear combination of thresholds. There is a good reason for that. It creates something called let. Okay, so I wanted to have my own wavelet, if you want. Okay, because I'm also a wavelet guy. I worked a lot in wavelet theory. So this is something that this is how I twisted somewhat the title. So now the most of what I'm going to talk to today is related to image denoising, image deconvolution, and also an algorithm for sparse image restoration. So, but all those techniques actually will use the same background, which is this thing that I call linear expansion of threshold. So, oops, please wake up. Okay, never mind. So, so there will be essentially three parts in this talk. One which will be the presentation of the technique, if you want. So I will try to emphasize what I call the functional formulation of the approach. Then I will come to what I call sure let algorithm. So there is a let here, which is this linear expansion of thresholds, and I will also mention this nice thing that is not very well known, at least in signal processing fields, which is an estimator of the MSE, the mean square error, when you have noisy data. So this thing is very interesting because it depends only on the noisy data that you have without any hypothesis on the background thing that you want to estimate. Okay, so I will apply this to image denoising and image deconvolution, or at least quickly, just to show you the technique. And then a completely different thing, which is try to solve an L1 minimization objective based again on this linear expansion of threshold. Okay, so first I will try to mention this this problem that is very frequent in image processing, which is image restoration. So we try very frequently to find a better image based on something that is convol, for example. Here I use the convolution problem, but it could be also a radon transform if you have images that come from computed tomography, from a scanner, for example. So whatever is linear, in a sense, gives you something plus noise, okay, gives you something like that. Okay, and the goal is to obtain the something that is as close as possible to the original. And then, okay, how to do that? Actually devise an algorithm that is able to provide that. Okay, so x hat here in this setting will always be the estimate. It's not the Fourier transform. Okay, there is no Fourier transform, so it's not exactly a harmonic analysis. I'm sorry about that, but this is more a bit statistical. Okay, a more general formulation here. If you see what I have done, you may believe that it's very general. Actually, it's not, because here I'm somewhat implicitly assuming that the noise is additive. Okay, and very often people would assume that it's also Gaussian, white, etc. Actually, a more general setting would be to say that what you observe, which is here, is actually related to, say, Hx, the thing that is not noisy, based on the probability density. Okay, so there are many techniques. So I will mention this one. So the Bayesian technique, which is which may either use maximum a posteriori, which is very frequently used nowadays in image processing. for doing lots of things, blind image deconvolution or whatever. So it's quite easy to set, but of course you have to put a very strong prior on what you want to find. Okay, so you maximize a conditional probability. Okay, there is another one which is less frequently used, which is the minimum MSE. Why is it less frequently used? It's because it's probably requires some more computations. Actually, it's very difficult to find the explicit minimum MSE. And it's also quite difficult to compute it approximately. Okay, the maximum a posteriori is easier. You try to find the maximum value, the maximum point of a probability density. But actually, by using an estimate of the MSE, it's possible to do this one. And actually, it's more interesting to do this one, at least if we want to compare with what people do in the literature, because in the end, they are going to compare signal-to-noise ratio, things that are related to the MSE, not to the maximum of some probability density. Okay, so then another approach is to forget about statistics and to say, okay, we are going to minimize this quantity. When I say forget about statistics, it's not completely right, because this can also be understood, you see, in a statistical framework. That is to say, this can be seen as, okay, if you choose the right prior, it can be brought back to a problem like that. Okay, but very frequently people prefer to understand it completely freely. Okay, like a data term plus a kind of regularization term, which in that case, okay, in more recent recent years, has been a sparse norm or sparsifying measure here. So it's not always a norm, because very frequently people want to have L0, which is not a norm, as everybody knows, but it can be transformed into something that is a norm, and actually that makes the thing here convex, so giving, allowing lots of algorithms to be applied here. Okay, so I will show how to minimize something like that using, once again, the let approach. Okay, so then you have many more techniques, in particular in signal processing, based on filtering. You know that if you filter an image that is noisy, then it looks already nice. This is one of the problems with beamers. They automatically filter images, so it's very difficult to show the quality of denoising algorithms in presentation, simply because there is already some kind of processing that is performed by beamers. And the most efficient techniques nowadays are, for example, the techniques based on non-local, maybe not this one, but patch-based, like BM3D, okay, which is quite a complicated technique. Okay, so the point here is that I would like to see image restoration as an approximation problem, not on X, but on the function that provides the estimate. So we are going to see this a bit later, but in most standard approaches, people see it more like an approximation of X, so they want to put hypothesis on X hat, etc., etc. So just an example, if I have a Laplace prior, okay, which will lead to something like L1 minimization, and I have additive Gaussian noise, okay, if I minimize, if I maximize, the posterior probability, then I will get something that is well known, which is the soft threshold. Okay, so I get an operation that is like that. Okay, if I try to find the best linear processing that can process my independent data here, I get a line. Okay, it's the Wiener solution. And now if I try to solve completely the MMSE problem, the minimizing the mean square estimates, then I get something that is not completely trivial, but still can be expressed using like error functions, okay? And that looks like that. So if you plot all the solutions together, you see that the Wiener is actually related to what happens for low intensities, low values. The map solution actually can care quite well for what is far away, for exceptional data. Okay. Okay, so I would like to see the problem, instead of a problem of estimating x hat, I would like to see it more as estimating the function that gives s hat. Okay, it looks a bit rhetoric, but actually this means that I'm going to put the emphasis not on how x hat behaves, okay, so the pixel-wise description, but more on how x hat would change if I would change slightly, for example, the observation y. Okay, this is important as we are going to see, because for finding the mean square, the estimate of the MSE, we will see that we are going to involve the divergence of this vector function here, so a kind of derivative of this. So how it changes with the input. Okay, and now what I'm going to do is use standard linear approximation techniques. That is to say that this f here can be expressed onto a basis. Okay, so of course I do not specify yet the basis, but this is the approach. So what happens is that functions, actually arbitrary functions, are almost arbitrary. It depends a bit on their regularity, but they can be efficiently approximated onto adapted bases. For example, you have standard bases like wavelets, sinks, you see radial basis functions, etc., etc. So if you put enough functions, then you approximate better. Okay. And actually, one of the points of one of the points that people have been looking at a lot in the past were actually how fast actually the approximation increases in quality when you put more functions, for example. Okay, here you have an example with the Laplace prior, okay, that I showed before, and on the same graph I put the approximation. Okay, so actually you don't see much differences. You may see that there is a kind of change here, but it's not very impressive. And actually this function can be expressed easily using three types of functions, which is not too surprising. One which is the line, another one that looks like this and this. Okay, it's just to show the idea of approximation here, and the idea that I would like to use now in order to approximate the processing. Okay, and it turns out that when you are doing image denoising, for example, what is going to happen is that you are going first a transformation, like a wavelet transformation. Why? It's because it makes lots of values small. Okay, very few large data, so it sparsifies the image. And so then, in the wavelet, in the transform domain, you would like to threshold things. That is to say, whatever is small, actually, it's probably in general noise or not very important. Okay, so you would like to set it to 0, and whatever is large or large enough, then you would like to keep it. So this is a very simple behavior. Okay, it looks like something that would behave essentially like the line plus a modification for small intensities. Okay, so this is why actually with very few terms like that, then in principle it should be possible to approximate the processing that you are going to do in wavelet subbands. So I'm anticipating a bit, but the theory in itself looks like that. The approximation of the processing can be expressed, for example, on a basis like that, where I have to specify the FK. And what I'm saying is that those FKs can be seen as thresholds, okay, in some transform domain. So this is why it's an expansion of thresholds. Okay, so the nice thing when you have a linear expression like that is that when you have a quadratic measure to minimize, and typically the MSE, the mean square error, or as we are going to see, the Schur, which is an estimate of this mean square error, which is also quadratic. When you minimize something quadratic for quadratic in coefficients, then you get a linear system of equations. This is very interesting algorithmically, because then it means solving a linear system of equations, which actually in that case will be small, so it's fast. Okay, fast, and also another thing, it's unique. Okay, unique up to a certain point, because in principle you may have a matrix that may be ill-conditioned, but if it is not, you have only one solution. Okay, when you have a processing that depends on non-linearly on parameters, then you are not certain of the unicity of the solution. Okay. So I will show the, oops, sorry. I will show the use of the LED for 3 different cases, as I said. So image denoising, deconvolution, and L1 minimization. So the first part is image denoising. So first let's have a look at the minimization of the MLC directly. So if I'm assuming that I know the original image, and I want to find the best linear expression of individual thresholding here that will fit my image, then, okay, the minimization leads to a linear system of equations to solve, okay? So I get something like that, and then if I develop slightly better, then the unknowns that are my interest, okay, the coefficients of the linear expansion are going to be expressed in a matrix form, okay, under this form. Okay, so I get something like that to solve. This is really very fast. Even if you have 100 coefficients here, if you try to solve in MATLAB linear system of equations with 100 unknowns, you will see that it's extremely fast. Okay, so now the main problem, of course, if I know X, I don't need to denoise, okay? So this thing has to be estimated because I know only the observation Y, okay? So how to do that? Then there is a very nice thing that is not well known, at least in my field, which is the unbiased risk estimate developed by Steins in the 70s, but published in 1981. So this is a very simple thing, okay? It's essentially, maybe I should give you the results. It is this quantity here, okay? So why? You have to remember that it is something that is random, because you have an original image, X, and you corrupt it by an additive noise, okay? And here, in order for things to work, you need to assume that this noise is additive, white, and Gaussian, okay? So once you have that, then it's possible to prove that the expectation, the mathematical expectation over all possible realizations of the noise of this thing is going to be exactly the same as the expectation of the mean square error. Okay? This is very, very powerful because now in this expression, as you can see, we have nowhere the knowledge of X, which is even better. There is absolutely no hypothesis on X in order to obtain this result. The only hypothesis relies upon the noise, which has to be additive, white, and Gaussian. And because of the Gaussian noise here, then you get this divergence here. This divergence actually comes from part integration, okay? So you have a Gaussian thing, you do part integration in an expectation, and you get directly this result. So it's something that any undergraduate can understand, and for some reason it's never taught, at least in my field, okay? One of the nice things here is that this quantity here, as you can see, it's like a norm. Divergence is also a sum of terms. So it's a sum of things, okay? And if you have n that is larger, if you sum up more things, you get always one number. So it gets closer and closer to the mathematical expectation that you have here. It's kind of a law of large numbers here. So this is particularly interesting for images because this n here is the number of pixels you have in an image. Okay, 65,000, 1 million, etc. So it's very, very close to the actual result. So just to summarize, no assumption on X are needed actually. Another thing that I like here is that the underlying signal here does not need to be random. You see, in Bayesian techniques, you need to put a strong prior on the underlying image. Okay, you have to say that, for example, it's wavelet coefficient follow a generalized Gaussian or something of the sort. This is not the case here. You don't even need this X to be random. So you can really process Lena knowing that Lena is unique. Okay. Okay, so then the operations are done in a transform domain, as I said. So usually we have a decomposition transformation, so discrete cosine transform, wavelet, etc. And you have a reconstruction linear transform, which is such that reconstruction, decomposition equals identity, okay? And the processing will look like that. So first you do the transformation, okay? Then you get wavelet coefficients. And this is where you are going to apply your nonlinear processing. But this nonlinear processing, as I have said, I'm going to decompose it into a sum of independent nonlinear processings, okay, on a basis, okay? And in the end, you do a reconstruction, okay? So if you look at the full picture there, then you see that the final basis that we are considering, okay, is not exactly the threshold that we have here, but something that is related to the threshold in the transform domain, okay? So we first do the decomposition, elementary threshold, and then reconstruction, okay? So this is one of the other aspects of this linear decomposition of threshold. It mixes very easily with what we would like to do usually, which is a linear transformation, okay? So then in the end, our elementary processings look more like that. So here you see there are no assumptions about R&D, except that they are somewhat inverse of each other. They may or may not be redundant. This is also another good thing because redundant processing actually involves lots of dependencies between subbands, which people are usually have difficulties usually to modelize. Okay, just an example first with a non-redundant wavelet transform, so which will put us close to what David Donohoe did more than 10 years ago. So assume that you are going to do some kind of simple thresholding, so pointwise thresholding of the wavelet coefficient, so one thresholding for each wavelet subband. Okay, so then if the transform is orthonormal, then it's possible to show that, like for the MSC, the Schur, okay, can be separated independently into subbands. That is to say, you can, if you want to minimize the full Schur, the full MSC if you want, of the processing, then you can do this independently subband per subband. Okay, so you have an expression that is like that, and you see the effect of the divergence now becomes a derivative. So then, because we have an we know that the processing should look like that, more or less, okay? Should be like the identity for large values and something flat, okay, close to 0 for small values, okay, to eliminate coefficients. Then we decided with my student at that time to use a kind of expression that depends on two bases, okay? One which is the line, another one which is something like the derivative of a Gaussian. Okay, and Schur shrink, you may have heard about that, was defined by Donohoe precisely to find the one parameter that he has in his processing, which is soft thresholding. So it depends on one parameter, which is the threshold, and to find the threshold that is here. So he decided to minimize the Schur, the estimate of the MSC, for this parameter. Okay, so it's not very different from Donohoe for the moment, and just to show you what it looks like, so you do first a wavelet decomposition, so you have one iteration, you do a simple thresholding, so then you eliminate lots of things there and there and there, and then you have a reconstruction, okay? So here the parameters of the decomposition, so A and B, so there are two parameters per subband, are actually optimized using by minimizing the Schur. Okay, so then you get here a small increase in SNR. If you do two iterations, the increase is substantially better. And if you do three iterations, you get even better. 4 iterations, okay, you tend to have a ceiling, okay, because simple thresholding is actually not very optimal, okay, in terms of using all the dependencies you may have in an image. Okay, so Donohoe would find slightly less good solution because the source threshold actually does something bad. Actually, at infinity, it shrinks. Okay, so probably this is the reason. Now we can also do undecimated wavelet thresholding, so redundant wavelets. Okay. So now we have observed that if we keep the same thresholding rule, then the results are not as good as if we use something that is more like a hard threshold. Okay. So slightly better, I would say. So, but it's interesting to use something that looks like that. As you can see, we have put a power 8 here, so which is quite dramatic. The goal is actually to create something that is almost Haar-like. The problem is that because we have to differentiate, the Schur is not the Haar threshold is not differentiable. So for this reason, we use a kind of approximation. Okay. So the optimal set is obtained like that. And how many parameters do we have to optimize now? It's essentially the number of iterations of the wavelet transform. So typically, say 5, okay, up to 5. Then you have 3 subbands in 2 dimensions, okay, H low, HH, low H. And then we have 2 parameters here for each subband. Okay, on the whole, it makes something like 30 parameters to find. So you have to solve a linear system of equations with 30 unknowns. The results are very good, actually, when you do that. So this is the result for Schur shrink, and this is the result you obtain if you use a simlet, okay, transform. You get something like okay, 2.5 dB more, okay, which is very substantial, and you see that the result looks quite good. Something that we observed actually is that if we use the Haar wavelet transform, then the results are even substantially better by more than 0.5 dB. So this tends to indicate that, okay, if you do redundant processing, maybe it's no use putting too much emphasis on the design of filters. Okay, so this is something that now I have been able to confirm for image deconvolution, etc. So and actually on the algorithms of other people like BLS, GSM, etc. Other algorithms, it's also the Haar decomposition that seems to be better. Okay, whereas it's well known that it's very far from the sync decomposition. Okay, so just a recapitulation of this, the Schurlet approach, and I have to go a bit faster because otherwise I will. So the idea is to find an approximation of the signal, actually to find an approximation of the processing, then minimize, for example, the objective function in that case, which is the Schur, and decompose the processing that we want to do into a linear sum of basis processing. Okay. Okay, so the good thing is that we get a fast algorithm, and the results are actually very competitive. So I can show you all the extensions that we have been working on with my PhD students in Switzerland some times ago. So multivariate thresholding, so when you take into account the neighbors inside subbands, okay, so you, the dependencies between subbands, so you get a better result already. Then multivariate, so the dependencies within subbands, so you see we gain something better. Then if we use redundant transformations, so using multivariate we get up to this. Then for some images we can use dictionaries of transform. There is nothing that says that we should use only a wavelet transform. We can use DCTs, etc. So if we use both of them, DCTs, wavelet transform, then so if we use only the wavelet transform, Haar wavelet transform, we get a certain result for this textured image, which is not very good. Okay, 26 dBs, no more. But if we use a dictionary using the block DCT, then suddenly we get much better. Okay. And multivariate case is also like that. We have also been able to process videos, so the gain is substantial also in that case. So I will skip the PKSNR comparisons, which if you are interested, I can show you later. Now I come to the convolution Schur. Okay. So the convolution Schur, it's the same idea, and actually, maybe naively, we could think that we should use exactly the same thing, because if you know a bit the proof for the Schur, you would understand that if you have a linear transformation on your data before adding the noise, then in principle, okay, we could get something very similar to the shore. It turns out that because at some point we need to do an inverse operation of the processing, things are not as simple as this. Okay, we need somewhat to do an inverse of the convolution, if you want. Okay, so for this reason, we need to define an approximate inverse here in order to have a processing that is stable. So the extended shore, I would say in that case, is not exactly an estimate of the MSE, but approximately an estimate of this MSE, provided that effectively the signal that we are looking for is, for example, low pass or something close to low pass, something like that. Okay. So then here we need then a kind of hypothesis on what we want to find. So it's not completely surprising here because effectively you see the operation H here may eliminate completely some information. So we need to care for something like that. So just to show you how it works on a simple thing, for example, Wiener deconvolution, which is not the best, okay, far from the best of what can be done. So if you want to do Wiener deconvolution, you have a parameter lambda that appears here, and usually you have a kind of regularization term that can be understood in a statistical sense. Okay, so you have a processing that is linear like that. So you have a matrix that appears here, and you have a parameter. So one way to do the best here, the best in this context here, is to minimize then the MSE that you would obtain over all possible lambdas. If you do that, it's a bit painful. Okay, but now if you say, okay, this processing here, I can express it as a sum of 3 different processings, for example, with different values of lambda, okay, with linear coefficients. So then you transform the nonlinear aspect of the problem into a linear aspect with maybe more parameters, but say 3 compared to 1. Then instead of solving a nonlinear optimization, non-quadratic optimization problem, you get back to a quadratic optimization problem with only one solution and a direct solution, direct explicit formula. So just to show you the type of results we have with that, this is the blurred image here with some noise. Okay, and here if we use 3 Wiener filters here, with varying coefficients here, optimized using the Schur, the convolution Schur, then we find something that is like that. Okay. Now, if we tune the lambda directly here, and we find the optimal Wiener filter, we get this result here. And as you can see, the result in terms of dBs are very, very similar. 0.01 dB in difference is nuts. Okay, nothing. So you can see also the differences here. So which are not obvious. Okay, so the Schurlet deconvolution consists in applying more generally. Okay, the Wiener deconvolution is not fantastic. So the idea is to do Wiener, then followed by some kind of denoising, wavelet denoising. Okay, so Wiener deconvolution looks like applying 3 Wiener filters, then perform an undecimated Haar wavelet thresholding, so to do the denoising. Okay. Then optimize the convolution Schur for the let parameters. Okay, so then the new basis looks more like that. So you have 3 Wiener filters. So this is the K that you have here. So K equals 1, 2, 3. Okay, you can have more if you want, but it does not bring much. And here the theta L correspond to the denoising part. Okay, so typically two denoising thresholds per subband. Okay, so on the whole we have 3 times more, okay, coefficients than what we would need for denoising, but it's still below 100. Okay, so it's still 100 by 100 system of equations to solve. So the typical results here are really reaching the state of the art. And they are actually much faster than most of the algorithms. So just to give you an idea, for a very standard PC, so the PC of my PhD student, which is not very fast, less than 1 second for a normal 256 by 256 image, it scales actually up by the number of pixels. So if you multiply by 4, if you multiply by 2 each dimensions. Okay? So just an idea of the algorithm, it looks like that. First, you have your observation. Then you do this multi-linear filtering. So you have 3 different linears, okay? So with 3 different values for the lambda. So 10 to the power minus 2, 10 to the power minus 3, 10 to the power minus 4, okay? Just to show you that they are not optimized, just like that. Then you have the underestimated wavelet transform, Haar wavelet transform. So you have all the subbands here plus the low pass, okay? Okay, so then you have the thresholding here, so elimination of a number of things, and then the reconstruction with the coefficients here. So the results are extremely good, and okay, very competitive with the literature. So just to show you the results, I'm not sure if anything can be seen here, but this is our results, and this is what actually one of the best results is BM3D usually. Yeah, but as you can see, it's a bit blurred here. And another result, which is more surprising for people who are used to total variation, etc. So they would expect for an image that is as simple as this, that total variation is the best. Actually, it is the best, but not by far, okay? Just by 0.05 dBs, something like that. So this is the kind of result that we can obtain. Okay, all the other algorithms are far away. Okay, so then the last part is something that that really I like a lot, because actually it makes it eliminates the link with the optimization measure. Okay, the optimized measure until now has been the Shure. Okay, so which is something that people don't know so well. But actually, it's not necessary to do that. If you do a linear expansion of threshold, you can optimize whatever you want, provided that, of course, the thing is nice enough. And in particular, I wanted in that case to optimize a convex measure like the L1 regularization, sparse norm or measure. I don't know how to call it. Okay, so the problem is always the same. Okay, you have restoration to do. Okay, so you measure distorted data plus noise, etc. But you don't have a statistical model anymore here. Okay, you just want to find the best fit that will sparsify the most somewhat your data. So you go in some transform domain. So W are actually transformed wavelet coefficients, for example, of the thing that you want to find. And you want to sparsify the most possible those wavelet coefficients. Okay, so you minimize this measure. You have a lambda, okay, that's maybe optimized or not. Okay. The state of the art here, or at least the things that are well known here, is first the IST iterative shrinkage algorithm here. So, okay, I'm not going to present it. Okay, it's not the goal here, and I probably don't have enough time anyway. There is what is known is that actually it's quite slow. Okay, you need to get a good solution. It's 500 iterations or so, something like that. Then there is a fast version of the IST that was devised more recently, so which is effectively faster, but not enough, so that people like Afonso and Figueiredo, actually I remember more Figueiredo than the first name here, use the splitting variable technique plus an augmented Lagrangian technique in order to have a much faster actually algorithm. So this is, I would say, somewhat the state of the art here in terms of speed. Okay, so the idea once again is to express the processing, so what gives you the solution of your minimization as a function of the observed data. Okay, but now because we are not probably going to find in one shot, okay, the exact solution, then it's necessary to think of an iterative scheme that allows to refine the thing. Okay, so here the idea is to use a basis that can be refined from iteration to iteration. Okay, so it's something like that. And okay, so now, the unknowns are those ones. And if this k is quite small, then it's very easy, actually, to find. And the k here will be something like 5. Okay? So we are going to see what are the conditions here in order to have something that converges, actually. So solving this for only 5 coefficients, it's a L1 problem with 5 linear things to find. So this can be solved very fastly using the iterative recursive least squares algorithm. Okay? So one of the nice things we have is actually a kind of unconditional convergence result. That is to say, if we include the equivalent of the solution that is in the IST. So I'm finishing actually. So if we include the solution that is in the IST algorithm, which is the soft threshold, amongst the solutions and also the original, the previous solutions, then actually you can prove that the algorithm converges unconditionally. If you know a bit the iterative shrinkage algorithm, you know that it does not converge unconditionally. You have a kind of parameter, a kind of step size in a gradient. That if it is too large, then the algorithm diverges. What happens is it's not the case here. And this is an example of what happens, okay, when you change the parameter that is equivalent to the IST here. Tau goes from 0.5 550, you see that it always looks like converging, whereas the IST would diverge for tau greater than 1 here. Okay, I'm going very fast. So anyway, by using this basis here, which includes also some kind of preconditioning here, so 5 bases on the whole, then the results are actually, you cannot read anything, but actually the results are always much faster than SALSA, for example. The numbers you have here are actually in hundreds of seconds, so 6 hundredths of seconds here for this kind of thing, 11 hundredths of seconds, etc. The comparison with SALSA, for example, is 100 hundredths of seconds. Okay, so this is for the underestimated wavelet, so it's slower but still faster than the other algorithms. So the number of iterations is actually very small. Okay, the criterion for stopping the iterations, because of course we stop, okay, is when we reach a solution that is closer to the ideal one, the final one. We effectively compute it by making 1 million or several million iterations of the FISTA algorithm when we are closer to by 40 dBs to the solution. Okay, so all the algorithms are treated similarly. Okay, and finally, to conclude my talk, I would like to thank my students, so Florian, okay, essentially, and Feng and Hanjie, which are my students at CUHK, and one of the papers we have produced on Shorlet, and the 2 papers that we have submitted for the last part of my talk. So that concludes my talk. I'm sorry for the delay. So that's it.